Beneath the familiar rhythm of heartbeat and breath lies a mystery so deep it unsettles even the world's most brilliant scientists. We know how to measure brainwaves, map neurons, and turn thought into code. Yet no one can explain why experience itself exists, why there is a you behind the eyes at all. Now, some physicists and neuroscientists are following an extraordinary trail into the quantum realm, where particles flicker between possibilities and reality itself seems unfinished until observed. Here, they've found clues in anesthetic rooms, meditation halls, migrating birds, and even green leaves drinking sunlight, hints that life may use strange, hidden physics to spark awareness. But if consciousness is tied to the quantum world, what does that mean for free will, identity, and what we really are? Step closer to the edge of the known and face the most intimate unknown of all, your own mind. A single heartbeat breaks the quiet. Slow and deliberate, as if sounding somewhere close, but not inside any chest you can name. Darkness stretches wide and heavy, the kind that makes shapes uncertain and air seem thick. There is the faint whisper of breath and the soft scrape of a sheet shifting as a body stirs. Caught in that place where night has not fully ended and day has not quite begun. Dreams linger like mist, faces half remembered, words slipping away as you reach for them, and yet there is also the slow, reluctant return of self, the moment you become aware you are awake. It is an old and private crossing, one each of us knows but cannot measure. For centuries, people have woken in this thin space and asked themselves the same silent question. What exactly is it that steps over the line from sleep into waking? What is the thing we call consciousness, and why does it remain so mysterious even now? There are no obvious clues in the room. A clock may tick. A neighbor's car may hum down the street. The floor beneath the bed is just wood and nails. And yet behind closed eyes, something impossible is happening. A presence forming, a point of view emerging from matter. Philosophers once called it the ghost in the machine, and long before there were machines at all. Storytellers imagined souls as birds or light or smoke that could leave the body behind. For centuries, thinkers tried to locate this awareness somewhere tangible. René Descartes sat by the fire in 1637 and wondered if the pineal gland might be its seat. Later, doctors studied damaged brains, mapping language to Broca's area, memory to the hippocampus, vision to the occipital lobe. And still, none of this answered the deeper question. Why does experience exist at all? How can cells and chemicals, no matter how complex, give rise to the quiet certainty that you are you? As science grew bolder in the 19th and early 20th centuries, the search widened. Men like Michael Faraday and James Clerk Maxwell uncovered invisible forces, fields of electricity and magnetism that could move metal and light up dark rooms. These discoveries taught us the world is not only what we see. Unseen layers hum beneath our ordinary senses. And then came a deeper shock. In the early 1900s, Max Planck introduced the quantum, tiny packets of energy, not smooth and continuous, but strange and granular. Albert Einstein revealed that light itself travels in little quanta called photons. Niels Bohr and Werner Heisenberg built a picture of matter that was far less solid than anyone had guessed. At the scale of the very small, certainty seemed to dissolve. A particle could be a wave. An event could exist in many states until observed. The world's fabric turned ghostly. It was in this strangeness that new whispers about the mind began to appear. If the building blocks of reality do not settle until someone looks, could looking itself consciousness be part of the story? Early quantum pioneers like John von Neumann and Eugene Wigner dared to ask such questions, though most physicists preferred not to follow them too far. The experiments, especially the double-slit test with its mysterious collapsing wave function, seem to say that observation changes outcomes. But no one could say what counts as an observer. Must it be a human mind? Could it be any interaction at all? The debate grew heated and then quieted, left to philosophers and dreamers for decades. Yet even as neuroscience advanced with brain scanners and electrodes, consciousness remained stubborn. By the 1970s, we could measure brainwaves and map them in real time. But we still could not explain why those waves felt like something. We could see neurons firing when someone looked at red or remembered a song, but we could not step inside their private view. The puzzle came to be called the hard problem, a phrase popularized by David Chalmers in the 1990s, and it continues to haunt scientists today. And so we return to that heartbeat in the dark, the breath before dawn. The idea that the key to understanding this experience might lie not in bigger machines or sharper scalpels, but in the very smallest scale of reality, has slowly gained a quiet following. Some suggest that inside the brain cells, deep and delicate structures called microtubules, quantum processes might flicker and hold sway before fading again, a kind of fragile computation hidden from ordinary physics. Others study how anesthesia, a drugged sleep with no dream, no time, no self, may shut down subtle quantum effects, turning off consciousness not by smashing it, but by disturbing its most delicate rhythms. These are still theories, not proven answers. Yet they hold out a strange hope. What keeps this search alive is the simple human fact of waking, again and again, into a world that feels both familiar and inexplicable. Each morning we slip back into a story that began before we were aware of it and will end without our permission. The thin curtain between sleep and waking is not just about rest and daylight. It is about the mystery of being a self at all, about how a universe made of particles and fields has found a way to look back at itself. If quantum physics tells us the world is more fluid and less certain than we thought, maybe it also leaves space for this quiet miracle, the return to ourselves every dawn, heart beating, breath rising, mind opening like a slow and silent door, salt wind pressed against the deck rails, damp and cold enough to sting the skin, as the young naturalist Charles Darwin stood leaning over the side of the small survey ship HMS Beagle in December of 1831. He was only 22, newly trained in theology and the study of the natural world, and not yet the man whose name would become tied to evolution itself. The ship rocked gently, bound for the coasts of South America, with a crew that worked by lamplight and salt lanterns, charts spread on a damp table below deck. Darwin carried notebooks already crowded with sketches of beetles and barnacles, rough notes about shells and bones. But when night came and the ship fell into a hush, broken only by the slap of waves and the sigh of rigging, he thought about something deeper than fossils or feathers. What made life alive? What stirred within the beating heart of a bird or the curious gaze of a monkey? Where did the thread of awareness begin? In those years, the word consciousness was not yet on every philosopher's page as it would be later. Thinkers still spoke of soul and spirit, of vital forces and breath. Ancient Greeks had imagined pneuma, a divine air flowing through living things. Medieval scholars had argued about the seat of the soul, whether it rested in the heart, the brain, or some finer hidden organ. In Darwin's own England, scientists like Thomas Willis and Robert Witt dissected animals searching for proof that nerves were channels for thought, but it was a world before neuroscience. Microscopes were still crude, and no one had yet traced the fine web of neurons that carry signals like sparks along living tissue. The brain was known to be important, yes, but not understood. Its wet folds seemed less like machinery and more like a mystery, a sealed chamber that somehow gave rise to dreaming and memory and pain. Darwin, for all his patient eye and love of collecting, was not immune to this wonder. In his later notes from the voyage, he wrote about the grandeur of life itself, not just its shapes and survival, but the strange pulse of it, the way organisms seemed driven from within. Watching finches on the Galapagos Islands in Iba Sanwu, he saw not just beaks adapted to seed or insect, but a hunger and cleverness behind the eyes, something no bone or feather could explain. Even a simple earthworm, which he studied for decades after returning home, seemed to display decision and purpose beyond mere reflex. These observations led him to a lifelong preoccupation. How could blind physical processes give rise to the living spark? Back in Europe, others shared the same quiet obsession. The German polymath Alexander von Humboldt, whom Darwin admired, spoke of Nattergold, the living picture of nature as one breathing whole. Physician-scientists tried to locate the animating force in animal electricity, following Luigi Galvani's jolting of frog legs in the 1790s. In Paris, Pierre Flourens carefully removed parts of animal brains to see which functions faded and which remained. Each experiment chipped at the puzzle, but none could show why experience itself, the warmth of sun. The sudden ache of loss should arise at all. As the 19th century turned, new tools appeared. Chemical dyes allowed early neurologists like Camillo Golgi to stain single neurons and watch their shapes under glass. By 1873, Golgi's black reaction revealed trees of nerve cells reaching like forests inside the skull. Later, Santiago Ramon Y. Kyle used these stains to draw breathtaking maps of brain pathways, each branch alive with silent signals. Yet even Kyle, father of modern neuroscience, admitted defeat before the question of how such cells create subjective experience. He could follow the wires, but not the light. This was the intellectual sea Darwin sailed on, though he did not know how far the ripples would go. His theory of natural selection, published in 1859, explained the shaping of life, but not the rising of mind. The question that lingered, as some historians now call it, remained untouched. How could matter wake up? The engines of survival could shape wings and eyes and clever hands, but could they also shape the inner flame that asks questions in dreams? The era's spiritualists offered one answer, holding seances and speaking of ether and unseen planes. Physiologists and early psychologists looked instead for measurable forces. By the time Sigmund Freud began probing the unconscious at the century's end, the idea that the mind might be partly hidden and partly knowable had taken hold, but still without a mechanism. The great voyage of understanding consciousness had only just left harbor, sails set but no clear map. What makes Darwin's time so haunting now is the sense of standing at a threshold. The Beagle returned to England in October 1836 after nearly 5 years at sea, its young passenger changed by jungles, deserts, and long nights of thinking. He carried trunks of bones and pressed plants, but also an unspoken wonder about the invisible breath inside all living things. That wonder would echo through later ages, into laboratories filled with microscopes, into hospitals searching for the edges of awareness, and eventually into physics, where the rules of the quantum would append every solid notion of reality. The voyage of the Beagle did not just set Darwin on the path to explain life's diversity. It also left behind a softer, quieter legacy. The enduring question of what it means to be alive and aware at all. And so, across the long years since that small ship pitched on gray Atlantic waves, the question has followed us like a patient tide. Every new discovery about cells and synapses, every strange glimpse into particles and fields, is in some way still answering a young man's silent thought as he leaned over the rails and looked into the deep. What lights the spark of life? What stirs and wakes behind our eyes? In the dim basement of the Royal Institution in London during the 1830s, air hung heavy with the scent of oil lamps and iron filings, and shadows trembled across walls lined with jars, coils, and glass tubes. Michael Faraday, lean and quick-eyed, though lacking formal schooling, moved quietly among his strange instruments. He wound copper wire into spirals, dipped iron rods into acid, and watched how sparks leapt like tiny living things between crude contacts. On the workbench lay delicate glass vessels filled with mercury and damp wool. In a corner, a great iron ring waited, wound with thick insulated wire, a silent promise of unseen power. Faraday's hands were steady, and his curiosity tireless. He had begun life as a bookbinder's apprentice. Devouring volumes he was meant only to stitch, and now he was prying at the invisible foundations of nature itself. One cold evening, he took a simple iron ring, wound 2 separate coils of copper around it, and connected one coil to a battery while leaving the other open. To the eye, nothing happened. The ring remained dark and still, but when Faraday quickly connected and disconnected the battery, a needle on a nearby galvanometer, a sensitive current detector twitched. A ghost of electricity had leaped across empty space from one coil to the other without any solid wire linking them. In that moment, Faraday glimpsed a hidden influence filling the air, a field that could carry force where no material touched. It was 1831, and though he lacked the polished mathematics of James Clerk Maxwell, Faraday's discovery of electromagnetic induction was a crack in the idea that the world was simple intangible. Something unseen and silent could reach, cross space and make metal needles move. Faraday's life's work unfolded in that basement, spinning copper discs, rotating magnets and mysterious lines of force drawn in chalk. The Victorian age was beginning to accept telegraphs and electric sparks, but his insistence that space itself was alive with fields was unsettling. People wanted the world to be made of parts like clockwork. Faraday saw something richer, a continuous influence humming behind appearances. His invisible lines would later become the language of Maxwell's equations and the groundwork for all modern physics. But to his contemporaries, they were almost mystical. Yet even as electricity and magnetism took hold of the imagination, giving rise to new machines and lighting cities, they remained predictable in their own way. A coil, a current, a field. Once you learned the rules, the forces could be tamed. The deeper mystery, however, was only waiting. By the end of the 19th century, the neat world of forces and particles began to crack. Physicists were proud of their success. Some declared that all of nature was nearly solved, that only a few clouds remained. But those clouds would change everything. In 1905, Albert Einstein showed that light, long treated as a wave, sometimes acts as a stream of tiny quanta called photons. A few years later, Max Planck's quantum of action and Niels Bohr's strange model of the atom hinted that electrons do not orbit like planets, leap and blur in ghostly probability clouds. And then came the experiment that turned curiosity to shock. Imagine a simple wall with two thin slits, and behind it a smooth screen ready to catch whatever comes through. Shine light or later even single electrons at the slits. If no one looks closely, a shimmering pattern of interference builds up on the screen, bright and dark bands like ripples on water, as if each particle spreads like a wave and interferes with itself. But when a detector is placed to watch which slit the particle passes through, the pattern vanishes. Instead of waves, you get two neat clumps, as if the particles suddenly decided to behave like tiny solid balls once observed. Remove the watchful eye, and the ghostly interference returns. It was not trickery. It happened again and again. It's confirmed by experiment after experiment. The double-slit result stunned early 20th century physics. How could a thing be both spread-out possibility and single particle, flipping nature depending on whether someone looked? And what counted as looking? Was it a human mind, or just the measuring device? Scientists like Heisenberg, Bohr, and later John Wheeler wrestled with this, inventing a new language of uncertainty and wave function collapse to cope with what their instruments showed. Yet the strangeness remained. The act of observation, or at least the act of measurement, seemed to help decide what was real, from Faraday's London basement to those quiet laboratories firing electrons one by one. The journey was longer than any single life, but threaded with the same shock. The world is not built of obvious bricks and gears. Fields invisible to the eye give rise to power. Particles obey rules only until they are looked at and then change. What began with a twitching needle became the foundation of quantum mechanics. A theory powerful enough to build computers and lasers, but still whispering that something essential about reality and perhaps about the minds that measure it remains. Unknown in the slow glow of lamps and later the sharp light of vacuum tubes. The quest moved from forces to something stranger, a universe where the very act of asking might shape the answer. And though scientists tried to keep their wonder in check, speak only of equations and instruments, a quiet unease settled in. If observation alters the fabric of the small, could it be that the consciousness asking, "What am I?" is not just a passenger, but somehow part of the machinery itself? The leap from Faraday's coils to quantum waves is vast, but both hum with the same warning. The visible is never all there is. The 20th century began with quiet confidence, the kind that comes from long success. For decades, science had seemed to tame the world. Steam and steel obeyed known laws. Electricity lit streets, and telegraphs carried words faster than any horse could run. Physics in particular felt nearly complete. Many believed that Newton's clockwork universe, polished by Maxwell's equations and the study of heat and light, was enough to explain whatever nature held. And yet, in small lecture halls and dim laboratories, cracks were already forming. In Berlin, at the turn of the century, a reserved man named Max Planck stared at numbers that refused to behave. He was studying the color of light radiated by hot metal. Something as ordinary as the red glow of an iron stove turning yellow, and then white as it heats. Classical physics predicted the wrong results. It even led to the absurd ultraviolet catastrophe, an impossible infinity of energy at short wavelengths. Planck, cautious and methodical, tried one last trick. He assumed energy did not flow smoothly like water, but came in tiny, indivisible packets, which he called quanta. On December 14, 1900, he presented the idea to the German Physical Society. He thought of it only as a mathematical fix, a reluctant patch. But that night, without knowing it, he had opened a door that would change how we understand everything. Soon after, Albert Einstein, then a young patent clerk in Bern, pushed the thought further. In 1905, he proposed that light itself could behave not just as a wave, but as discrete little bundles of energy later called photons. He used this to explain the photoelectric effect, where light striking metal kicks out electrons with a sharp threshold, something no wave theory alone could predict. That simple explanation earned him the Nobel Prize and showed the world that Planck's trick was more than bookkeeping. It described reality. Even light, the most ancient symbol of purity and continuity, could come chopped into ghostly quanta. From there, the fractures widened. Experiments with electrons, atoms, and radiation produced results that made seasoned scientists doubt their senses. Imagine a lab with bare bulbs flickering above brass instruments, the faint smell of ozone, and metal filings in the air. Counters clicked as radioactive particles flew unseen. Cloud chambers revealed faint silver threads where invisible particles passed, curling and vanishing like smoke. In these spaces, the familiar world of billiard balls and planets gave way to something twitching, unpredictable, alive in its own strange way. Werner Heisenberg, a brilliant and restless young German physicist, faced this strangeness directly in 1927. He found that certain pairs of measurements, like where a particle is and how fast it moves, cannot both be known with unlimited precision. The more carefully you measure one, the fuzzier the other becomes. This was not a flaw in instruments, but a basic feature of nature. He called it the uncertainty principle. At the smallest scales, reality refused to settle until it must, and even then it seemed to settle only provisionally, more like a murmur than a shout. Niels Bohr, Heisenberg's mentor in Copenhagen, spoke of complementarity, the idea that matter sometimes acts like a particle, sometimes like a wave, and we must accept both pictures even though they seem to contradict each other. The old dream of a single clear description shattered. To know the world, we had to live with paradox. For anyone raised on the solid rules of classical physics, this new vision was unnerving. Yet it worked. Quantum theory predicted with uncanny accuracy the colors of atoms, the bonding of molecules, the behavior of semiconductors and lasers long before they existed. The deeper the success, the sharper the puzzle became. If the foundation of matter is a haze of probabilities and sudden jumps, then the clear, continuous flow we feel in everyday life is some kind of surface illusion. Beneath the wood of the table and the bones in our hands, beneath the familiar beat of the heart, lies a world that is not certain. Not settled until something happens, perhaps until it is touched, measured, or even simply observed. It is here, in this uneasy space, that the question of consciousness flickers again. If electrons and photons do not have fixed properties until an act of measurement, and if the very fabric of reality hesitates before becoming definite, could the mind, whatever it is, be tied to this hesitation? Could awareness itself be the final observer, coaxing a blur of possibility into a single experienced moment? These are not conclusions most physicists like to claim, but they are whispers that refuse to fade. Picture a quiet experimental hall. In the 1930s, a single hanging lamp, the scent of varnished wood, the steady tick of a Geiger counter. A scientist leans close to a small glowing tube where electrons move. Aware that equations can describe the probabilities, but not the moment one particle will appear. Now imagine your own mind, aware of itself, trying to be sure of its own edges, and feeling them slip. The thought is unsettling, but also strangely beautiful. If the base of matter is not solid, perhaps it is not surprising that the base of self is slippery too. Max Planck himself grew philosophical as he aged. Speaking of consciousness as fundamental and matter as derivative, Einstein stayed cautious, but admitted unease at the dice-throwing universe. Bohr counseled humility, saying that those not shocked by quantum theory had not understood it. None of them solved the mind's riddle, but their work changed the kind of riddle we are asking. The solid world cracked open into waves and quanta, and suddenly, the mystery of awareness no longer seemed to live in a special soul stuff alone. It seemed to share its strangeness with the universe itself, and so the curtains split. Behind the familiar world of light and warmth lay a place where certainty is rare, where observation matters, where being seems to emerge from possibility. It is a world we still struggle to describe without stumbling into poetry, because ordinary language, like ordinary physics, was built for heavier, slower things. Yet we know this new world is real. Its mathematics builds our technologies, its quirks light up our screens, and somewhere inside each of us, an unseen spark turns sensations into self, questions into thought, silence into awareness. Whether quantum rules play a part in that turning, we still do not know. But once the curtain was pulled back, it was impossible not to wonder if the same deep strangeness shaping atoms also shapes the waking mind. It begins simply. So simply that for a long time no one expected it to hold any mystery at all. Imagine a plain metal plate with two narrow slits cut side by side, and, a few feet beyond, a smooth screen ready to record whatever passes through. At first, the experimenters used beams of light because light was already known to behave like a wave in many ways. When the beam shines on the slits, something elegant appears on the screen, a pattern of bright and dark bands. The sort you see if you drop two stones in a pond and watch the ripples collide. Each slit sends out its own wavefront of light, and where the waves meet in step, they shine brighter. Where one crest meets another's trough, they cancel and fade to darkness. It is beautiful and easy to grasp, a sign that light spreads and interferes with itself like water. Then came a question. If light is made of tiny particles, as Einstein's photoelectric work suggested, these quanta we call photons, what happens if you send them one by one? The answer seems straightforward. Each photon is a little bullet of light. Surely two slits would just mean two fuzzy piles on the screen. But that is not what happened. Even when the photons were spaced out so far apart that no two could possibly touch or talk to each other, the pattern of waves still emerged, slow but undeniable. Point by point, building the same delicate interference fringes, it was as if each photon passed through both slits at once, interfering with itself. Splitting and rejoining before arriving, physicists stared and recalculated. Perhaps some hidden medium was guiding the photons, some secret whisper between them. But no, every test they devised failed to catch any such signal. The pattern seemed to form because the world at this scale does not choose a single path until forced to. The photon remains in a spread of possibilities, a haze of maybes, till something compels a decision. That something was the next revelation. If the experimenters set up a simple detector at the slits to check which path each photon took, nothing elaborate, it's just a way to know left or right, the magic vanished. Suddenly, the interference pattern collapsed. Instead of many thin, bright lines across the screen, there were just two blurry clumps, as if each photon had picked one slit and marched through like a tiny bead. Remove the detector, let the photons travel unseen, and the strange wave pattern returned. It was as if the mere act of knowing forced the photon to decide. Collapsing the shimmering spread of options into one reality, this result was confirmed over and over. With electrons, neutrons, even huge molecules of carbon and hydrogen, it became the beating heart of quantum theory, the idea that before measurement, a system exists in a superposition, many possible states at once, and that measurement selects a single outcome. Yet what counts as measurement? Is it just any physical interaction, like the bump of a stray air molecule or a flash of light? Or is there something deeper about awareness, about an observer in the truest sense? Early pioneers wrestled with this question uneasily. Niels Bohr and his Copenhagen Circle insisted that the math was clear: observation ends superposition. But observation might mean any interaction that records a fact in the world. John von Neumann's rigorous proofs suggested that, strictly speaking, the chain of measurement could keep moving, from the detector to the electronics to the scientist's eye, and nowhere does the theory say where it must stop. Eugene Wigner dared to say aloud what others whispered: perhaps consciousness itself is the final boundary, the place where probabilities become a single experienced reality. That thought thrilled some and offended many, but it refused to go away in a quiet laboratory. The scene can feel almost supernatural despite the wires and lenses. A lone photon gun clicks softly, sending tiny bursts toward the slits. The room is dim, with red safety lamps glowing like coals. On the far wall, a screen records faint speckles of light, each one meaningless alone, but together slowly forming a pattern that should not exist if the photon were just a little bead of matter. Then the detector is switched on, a faint relay clicks, and the pattern begins to blur into two dull heaps. Knowledge has entered the system, and the strange beauty drains away. For those who stand and watch, the experience is unsettling because it suggests that reality at its base does not behave until someone or something asks it to. The everyday world seems solid and definite. Yet here is proof that deep down, things hover in uncertainty, ready to be many until they must be one. And it is our act of looking, or at least our insistence on knowing, that seems to press them into shape. Some scientists avoid philosophical leaps and call this just a quirk of quantum information. Interaction creates records. Records create facts, and there is no need to mention consciousness at all. Others point out how slippery measurement becomes once you try to pin it down. Still others, especially those interested in the great unsolved problem of the mind, cannot help but wonder if this puzzle hints that awareness is not a bystander, but somehow woven into the universe's rules. If the mind itself is made of quantum matter, perhaps its strangeness is no accident. From the simple sight of ripples behind two slits came a revolution. It taught us that certainty is late to arrive, that the world prefers possibilities until forced to choose. And standing before that faint glowing pattern, one cannot help but feel the echo of a deeper question. When we open our eyes each morning, are we only watching? Or are we also, in some profound way, helping the world decide what is real? In the late 1970s, tucked away on the quiet, tree-lined campus of Princeton University, a curious laboratory began to hum with a different sort of question than those that usually filled the engineering halls. It was an age still touched by the restless afterglow of the space race, when computers were bulky and beige, and when the belief that technology could solve nearly anything ran strong. Yet inside a nondescript building, behind doors marked with nothing grand, an experiment took shape that many found too strange to speak of openly. It was called the Princeton Engineering Anomalies Research Lab, or simply PEAR, and its mission was not to build faster machines or stronger bridges, but to probe whether the human mind could reach beyond its skull and gently tilt the odds of the physical world. The founder was Robert Jahn, an accomplished plasma physicist and dean of the School of Engineering and Applied Science. Jahn was no fringe thinker. He had spent years working with high-powered propulsion systems, including those tied to NASA's hopes for deep space travel. But when a curious undergraduate named Brenda Dunn came to him with questions about consciousness and machines, questions most professors would have waved away, Jahn surprised himself by listening. He was intrigued by the possibility that there might be small but measurable ways in which intention, a focused act of mind, could leave fingerprints on random events. And so, in 1979, the PEAR Lab opened quietly. With funding scraped together, in a single small room filled with odd contraptions, at the heart of the lab sat a simple device that looked almost like a toy, but was anything but trivial: a random event generator. In those days, it was often a small box with blinking lights, inside which electrons danced through a circuit to produce sequences of ones and zeros that should, by all known physics, be utterly unpredictable. Each run of the machine was supposed to balance perfectly over time half ones. Half zeros, the digital version of a coin flipped again and again in a vacuum. The task given to volunteers was deceptively simple. They would sit in front of the machine, sometimes with eyes closed, sometimes staring at the lights, and try to nudge the output ever so slightly away from pure chance. Push, with thought alone, for more ones than zeros, or the other way around. There was no trick, no physical contact, no hidden controls. Just quiet focus and a printout at the end. Day after day, year after year, thousands of trials accumulated. Students stopped by between classes, faculty came out of curiosity, visitors wandered in. Most sessions ended with nothing unusual. The numbers obeyed the normal drift of randomness. But sprinkled through the growing mountain of data were results that refused to smooth away tiny but statistically odd deviations. As if intention had left the faintest breath on the dice. Sometimes the effect was so small, it would vanish with just a few sessions of bad luck. Yet when the data were pooled across long months, the patterns held enough to trouble strict skepticism. The atmosphere in the lab was a mixture of quiet excitement and relentless doubt. Jan and Dunn insisted on rigorous controls, shielding machines, keeping records meticulous, inviting outside statisticians to check their math. They knew the danger of wishful thinking and the reputation of parapsychology as a field riddled with self-deception. Still, the whisper persisted. Maybe something is happening here. The volunteers often reported odd subjective feelings, a sense of merging with the machine, a strange calm or vivid imagery. Some felt nothing at all, just mild curiosity and then surprise when their session logs showed improbable streaks. Outside the lab, reaction was sharp and often scornful. Many physicists dismissed the work as an unfortunate detour for a respected engineer. Letters arrived suggesting Jan had lost his way. Yet others, though unconvinced, were intrigued by his care in running the studies. Here was no carnival demonstration but serious apparatus, clean statistics, years of data. Even so, the idea that mind could bend chance was too radical to accept easily. It poked at the clean border between subject and object that modern science had drawn since Descartes. For students who stumbled into the lab, the place felt oddly timeless. There were humming machines, the faint smell of warm electronics, shelves of neatly labeled tapes and printouts, and the low, thoughtful voices of people asking questions most classrooms ignored. You might hear the clack of a keyboard as another sequence of random bits scrolled out, and someone quietly wondering what it meant if will alone could tilt a machine by a hair's breadth. Could consciousness be more than a passenger? Was there some thin, unmeasured channel linking intention and matter? Over the years, PEAR expanded its methods, adding experiments with falling balls and slanted bins, water fountains with unpredictable splashes, and even remote attempts where participants tried to influence devices from far away. The results never became spectacular enough to silence critics, but they also never vanished into pure noise. They remained at the edge, improbable yet persistent, like a rumor that refuses to die. Jan himself admitted the effects were small and the implications murky. But he believed it was unwise to look away just because the phenomenon was faint. By the time the lab finally closed in 2007, it had gathered nearly 3 decades of data and left behind a complicated legacy. For some, it stood as a cautionary tale about venturing too far into the unknown. For others, it was a quiet monument to intellectual courage, a reminder that asking if mind and matter touch might be uncomfortable but not unscientific. And perhaps most interesting of all, it created a bridge, however fragile, between hard physics and the elusive question of consciousness. Looking back, the PEAR experiments did not solve the riddle of awareness or prove that thought shapes reality in any grand way, but they left an impression that lingers, a whisper carried forward into other corners of research. If random machines can sometimes seem to answer the human mind, if only by the thinnest statistical edge, then the clean wall we place between self and world may not be as solid as we like to think. In a quiet Princeton basement, amid blinking lights and cautious notes, a daring idea took its first careful steps. Maybe the reach of consciousness is not yet fully known, and maybe the smallest cracks in chance are worth watching. In the hushed stillness of an intensive care ward, where the lights never fully dim and the air smells faintly of antiseptic and warmed plastic, a body lies quiet under a pale blue sheet, monitors tracing thin green lines across a dark screen. It is here, among ventilators and the soft shuffle of nurses' shoes, that one of medicine's deepest puzzles first began to press itself into the scientific conversation about consciousness. For decades, physicians had assumed that when the brain is deprived of oxygen and electrical activity seems to stop, awareness itself must vanish, that death of experience arrives before the body's final end. Yet scattered stories from these rooms suggested something stranger. Patients who had been pronounced clinically dead for minutes, their hearts still, their brains silent by all standard measures, returned later to speak of scenes and sounds that should have been impossible to witness. One of the earliest modern sparks came in 1975, when cardiologist Raymond Moody collected accounts from people who had survived close brushes with death. He described reports of floating above the operating table, of hearing conversations among surgeons, of moving through darkness toward light. At first, these stories were treated as comforting but unreliable. The brain's final fireworks as cells starved and hallucinated. But then, in the 1980s and 1990s, better tools allowed physicians to measure electrical activity with precision. The pattern of silence during cardiac arrest became clear. After about 20 seconds without a heartbeat, the brain's measurable signals collapse. After a minute, there is no organized activity left. And yet survivors occasionally return with memories that lined up with real events, details of equipment, snatches of dialogue, even small visual facts that seemed to match what staff were doing while the patient was, by all instruments, gone. One such case, often told quietly among researchers, involved a woman in Seattle who arrested during a surgical procedure and was later revived. She recounted a vivid moment of floating, of watching her own body, seeing a nurse drop an instrument that clattered to the floor. When staff compared her account to the room's events, it matched, though she had been deeply anesthetized and without heartbeat at the time. Another story came from a man who described a red shoe on a hospital ledge outside the operating suite. Later, curious staff checked and found it just where he said. Skeptics pointed out that details can be guessed or remembered wrong, but the sheer number of such reports began to trouble easy dismissal. In the early 2000s, these stories drew serious study. British physician Sam Parnia and his team launched the AYRE Awareness During Resuscitation project, placing hidden images in emergency rooms and cardiac wards and later interviewing revived patients. While few participants could describe the images, evidence remained thin. Some produced verifiable accounts of events during periods when their brains were expected to be completely offline. One man accurately recalled the automated external defibrillator's sounds in a nurse's remarks. During 3 minutes of flat electroencephalogram, something thought impossible under traditional neuroscience. These findings did not prove that consciousness floats free from the body. They did, however, press a sharp question into view. If the physical activity that is supposed to generate experience is absent, what exactly is remembering? Are there unknown forms of brain activity we have yet to detect? Faint, quantum-level patterns, perhaps that persist after large-scale signals stop? Or does consciousness have some other footing we do not yet grasp? At the same time, studies of deep anesthesia offered their own quiet shocks. Anesthesiologists long believed that adequate doses reliably erase awareness, yet patient reports told a more complex story. Some emerged after surgery recalling voices or sensations when their vital signs and brain monitors suggested total unconsciousness. Experiments in the 1990s and early 2000s began to show that while the cortex may shut down obvious patterns, small regions can remain active, as though a pilot light still flickers even in deep sedation. If so, perhaps our understanding of when and how the light of consciousness extinguishes is incomplete. For philosophers and scientists alike, these hospital stories were unsettling, not because they proved life beyond death, a leap no careful researcher claims, but because they revealed blind spots in our maps of mind and brain. If experience can surface when the usual machinery is down, perhaps the machinery is more subtle than we think. Some theorists suggest networks of neurons might retain fleeting quantum coherence even after gross signals fade. A conjecture still controversial, but no longer laughed out of the room. Others wonder if consciousness can be understood as a process that does not require constant, large-scale firing, but can persist in hidden, quiet states. Within the wards themselves, the human impact was immediate. Nurses and doctors who heard these accounts sometimes softened their certainty about the boundary between alive and gone. Resuscitation teams began paying more attention to the possibility that patients might have inner experience during cardiac arrest or surgery, even if they could not show it at the time. Families, hearing survivors speak of warmth, light, or watching over loved ones, found comfort. Clinicians found unease, but also curiosity. By the time this wave of study reached journals and conferences, the conversation about consciousness had shifted. It was no longer enough to say that the brain simply stops and the self disappears like a candle blown out. Data, however rare and fragile, suggested something else may happen, something we do not yet measure well. And for those already exploring how quantum processes might underpin awareness, these hospital rooms seem to open a crack in the door. If consciousness can hang on when gross neural firing is absent, maybe it is not bound in the way we thought. Maybe the dance of experience is subtler, harder to snuff out, and possibly rooted in physics we have not yet mastered. No matter where one stands, skeptic or seeker, the stories persist. A patient wakes and speaks of floating near the ceiling. Another recalls the voice of a surgeon, murmuring an aside no one thought he could hear. Machines and monitors say there was no mind there, yet something observed and later returned to tell. The debate remains fierce, but the quiet power of these accounts is undeniable. They remind us that the line between nothingness and awareness may be thinner than our current instruments can trace, and that somewhere in the space between heartbeat and silence, a deeper truth about consciousness waits to be found in the last decades of the 20th century. When neuroscience had mapped more and more of the brain's outward wiring, but still could not explain why any of it felt like something, an unlikely partnership formed across two very different worlds. One was the quiet office of Sir Roger Penrose at the University of Oxford, a mathematician and physicist known for shaping our understanding of black holes and the deep geometry of space and time. The other was the operating theaters and research rooms of Dr. Stuart Hameroff, an American anesthesiologist at the University of Arizona who had spent years watching people slip into and out of consciousness under carefully measured doses of gas and drugs. Their meeting was improbable. One worked among chalkboards and equations, the other among ventilators and the smell of sterilized steel. Yet both men were drawn to the same unsolved riddle. How do brains produce the first-person experience we call mind? Penrose had long felt uneasy with the idea that ordinary computation, even vast neural networks, could explain awareness. In 1989, he published The Emperor's New Mind, arguing that something about human thought seemed to transcend algorithms, as if our minds were not just machines running code. He speculated that quantum physics, the bizarre world of superpositions and collapses, might hold a missing key. Hameroff, meanwhile, had spent his career chasing a more practical mystery: how anesthesia works. A few breaths of certain gases, or a slow drip of propofol, and consciousness simply disappears. Patients' brains still fire in scattered ways, but the coherent, unified field of self and time is gone. When they wake, it returns in a rush. For Hameroff, this implied that whatever produces awareness is fragile and can be disrupted in a subtle way, perhaps far below the level of synapses and large circuits in the early 1990s. After reading Penrose's book, Hameroff reached out. He had long been fascinated by the inner scaffolding of neurons, those tiny cylindrical proteins called microtubules that form intricate lattices inside cells. Most neuroscientists regarded them as mere structural support, little struts keeping cells in shape and shuttling molecules back and forth. But Hameroff suspected they might be far more dynamic and sensitive than assumed. Microtubules are built from tubulin proteins that can exist in different states and pack into beautiful hexagonal arrays. Hameroff wondered whether quantum events, coherent vibrations, Fleeting entanglement could occur within this protected interior, hidden from the noisy environment that usually destroys quantum effects in warm, wet places like the brain. Penrose found the idea enticing. He had been searching for a physical site where his concept of objective reduction, a natural, gravity-related collapse of quantum states, might take place in a way that could influence neural activity. Together, the two men developed what they called ORC, or short for orchestrated objective reduction. In their view, microtubules could maintain delicate quantum superpositions for tiny fractions of a second. And then, when a certain threshold was reached, those superpositions would self-collapse, not because of a measuring device, because of a fundamental instability in space-time itself. Each collapse, they proposed, could correspond to a moment of conscious experience, like a flicker or a frame in the movie of awareness. The orchestrated part referred to the idea that neurons might tune or influence these events, shaping them into the coherent flow of thought and sensation. It was a daring theory and met at once with skepticism. Most physicists believed quantum coherence could not survive in the warm, wet brain for even a nanosecond. Decoherence, the loss of fragile quantum states, should be near instant. And many neuroscientists felt the proposal was an unnecessary leap when so much about conventional brain function was still unexplained. Yet Penrose and Hameroff pressed on. They pointed to intriguing findings. Certain anesthetic molecules seemed to bind strongly to tubulin proteins, hinting that disturbing microtubules might indeed silence awareness. There were also studies showing that microtubules can oscillate and conduct electrical activity in ways not yet fully charted. Over the years, small but suggestive pieces of evidence emerged. Experiments showed that photosynthesis in plants, bird navigation, and even the human sense of smell may use quantum effects in warm, messy environments once thought impossible for such delicate physics. If leaves and birds can shelter quantum processes, why not neurons? Advances in imaging revealed microtubules to be more dynamic and information-rich than simple scaffolding, capable of complex patterning. Meanwhile, the mystery of anesthesia deepened. It remained hard to explain how shutting down awareness could be so fast and reversible if it were just about silencing huge networks. Still, man's kept its guard. ORC, many argued, might be more poetry than physics until clear experimental proof arrives. Critics point out that even if microtubules host quantum events, connecting those directly to subjective experience is another leap. Penrose himself admits the bridge between equations and the glow of being alive remains speculative. Yet, the theory has not faded. Instead, it has found a small but persistent community of researchers exploring quantum biology and the fine interior of neurons. Hameroff continues to publish on how anesthesia could work by dampening quantum vibrations in microtubules. Penrose refines his ideas about objective reduction, seeking ways to test whether space-time instability might be felt inside cells. They host conferences where physicists and neuroscientists, often uneasy allies, argue late into the night about coherence times, tubular networks, and the felt sense of self. What matters, perhaps, is less whether ORC is proven than what it symbolizes. A willingness to look beyond familiar wiring diagrams and acknowledge that the mystery of consciousness may require physics as strange as the mind itself. It reminds us that our brains are not just tangled meat but exquisite physical systems shaped by billions of years, maybe capable of feats we have not yet named. It also touches something older and more human, the suspicion that the self, the quiet interior life we each carry, is not just an accidental byproduct, but tied to the fabric of reality in ways we do not yet understand. In this way, the microtubule mystery is both humbling and thrilling. It does not promise easy answers or magical powers, only a deeper invitation to study, to imagine, and to listen more closely to what our cells might be whispering. Somewhere in those protein lattice, flickering at the edge of physics, there may be moments when the possible collapses into the felt, when mere matter becomes a single conscious instant, and then another, and another, until a life unfolds. Thinking and feeling and asking how such a thing can be in the softly humming corridors of modern hospitals, where machines blink and whisper like patient guardians and the scent of antiseptic mingles with warm blankets and oxygen. An extraordinary fact sits hidden behind routine. Every day across the world, anesthesiologists walk patients across the thin bridge between full, alert selfhood and the deep, wordless dark of surgical sleep. They do it with astonishing reliability. A few milliliters of clear liquid entering a vein, a cool rush in the arm. Count backwards from 10, and the vibrant, layered experience of being alive is gone. Not scrambled or dreamlike, but truly gone. Time stops. The self disappears so completely that when the patient returns, they often remark on the nothingness as if no time had passed at all. It is a small miracle and a quiet warning. The thing we call consciousness, so rich and stubborn, can be silenced with shocking ease. For decades, doctors knew this in practice, but not in principle. The first modern general anesthetic was administered in 1846 at Massachusetts General Hospital by William T.G. Morton. And the gas ether soon transformed surgery from a brutal ordeal into something survivable. Yet no one truly understood how these invisible agents worked. Over the following century, chloroform, nitrous oxide, halothane, and newer halogenated ethers came into use. By the mid-20th century, drugs, like propofol and sevoflurane, joined the armory. All of them could suspend awareness and pain while leaving the body alive and maintainable. But despite advances in neuroscience, the deeper mechanism of how they switch off the subjective world remained elusive. By the 1990s, brain imaging had advanced enough to watch neural activity during anesthesia. Functional MRI and EEG revealed that these drugs did not simply shut down the entire brain like turning off a light. Many circuits kept firing. Sensory regions might still respond faintly, and brainstem centers still kept breathing and heartbeat steady. Instead, anesthetics seemed to disrupt communication among distributed regions, especially the networks that tie perception, memory, and self-awareness together. Coherence, the synchronized rhythms of millions of neurons, unraveled. Yet even these findings left an odd unease. The brain was still electrically active, but the rich film of consciousness had vanished. The question sharpened: what exactly had been silenced? Into this puzzle came a line of thought that quietly intersected with Roger Penrose and Stuart Hameroff's speculations. Hameroff, the anesthesiologist turned consciousness theorist, had long noticed that many anesthetics, though chemically different, share a curious trait: they bind strongly to certain proteins inside neurons, especially tubulin, the building block of microtubules. Microtubules, usually dismissed as scaffolding, form intricate networks inside every nerve cell. If, as Hameroff and Penrose suggested, these structures might host delicate quantum processes, fleeting states of superposition, somehow woven into brain function, then disrupting, them could in theory silence the flicker of conscious moments without needing to paralyze the entire nervous system. Anesthetic molecules could be scrambling quantum-level order deep inside cells, a subtle sabotage far beneath the familiar circuits and synapses. The idea seemed fanciful when first proposed, yet the practical clues refused to go away. In 2001, studies on anesthetic potency and protein binding showed correlations hinting that what mattered was not only broad neuronal shutdown, but tiny interactions with hydrophobic pockets in tubulin. Other research found that microtubules can resonate and vibrate at high frequencies, potentially sensitive to interference. Even mainstream anesthesiology began to speak of quantum channels not as proven fact but as a possible part of the puzzle, at least worth investigating. The ease with which consciousness disappears under anesthesia made more sense if its underlying architecture is fragile, built on coherent but easily disturbed events. For Penrose, whose theory of orchestrated objective reduction had been criticized as impossible in the warm, wet, noisy environment of the brain, these clinical facts felt quietly supportive. If ordinary drugs can end subjective experience without shutting down metabolism or simple reflexes, then perhaps consciousness indeed depends on a subtle layer that can be tipped out of order before the obvious machinery stops. The operating room became an unintentional proving ground. Each time a patient slid into blankness within seconds of an injection, the mystery deepened, but also pointed somewhere specific, to molecular and possibly quantum underpinnings. The effect on scientific conversation was subtle, but real. Where once Orkawar was dismissed with near laughter, now more voices urged caution before declaring it impossible. Physics had already revealed examples of delicate coherence surviving inside living systems. The energy transfer in photosynthesis uses quantum wave-like behavior to find efficient paths. The strange compass sense of migratory birds, likely rooted in quantum entanglement inside proteins. Warm, wet biology might not be as hostile to quantum order as once assumed. If plants and birds could harness such physics, perhaps neurons could too. And anesthesia could be our everyday proof of how easily that order can fail in hospital practice. These debates remain far from the surface. For patients, anesthesia is simply merciful. Yet every quiet induction, the soft reassurance of the anesthesiologist, the beep of the monitor slowing into a steady line, the world blinking out is also a profound data point. Here is consciousness. Vast and personal, switched off like a lamp. Here is a clue too important to ignore. When Penrose and Hammeroff point to this, they do not claim victory. Their theory is still bold and far from proven. But the anesthetic clue keeps it alive. It suggests that awareness is not just a side effect of electrical chatter, but something emergent from fragile physical states that can be subtly destabilized. And if that is true, then consciousness may be less like a storm of neurons and more like a delicate quantum dance taking place inside them. A dance that can stumble with a small chemical nudge. This possibility invites humility. We build whole lives on our sense of self, yet it can vanish in a breath of vapor or a slow drip of milky white propofol. At the same time, it invites wonder. If our most intimate experience depends on fine physical coherence, it means the fabric of mind might be closer to the deepest fabric of the universe than we imagined. Somewhere between the cool touch of an IV and the blank space before waking, a window opens briefly on how mysterious and subtle consciousness really is. And when we wake again, often with no memory of the hours lost, we are left with a renewed sense of how fragile and how extraordinary awareness must be. On a crisp autumn evening in 2015, the long glass corridors of Delft University of Technology glowed faintly against the Dutch dusk, their windows bright squares set among brick and quiet canals. Inside, in a physics lab, layered with cables and careful shielding, a small team of researchers prepared to test something that had haunted science for almost a century. They were not chasing metaphors or easy wonder. They were chasing proof. Ever since Albert Einstein had scoffed at what he called spooky action at a distance, the idea that two particles could remain mysteriously linked across space, quantum entanglement had been both fascinating and suspect. Many physicists trusted it, having seen its strange predictions confirmed again and again. But there was always room for a critic to say the experiments had loopholes, tiny gaps where hidden signals might sneak through. That night in Delft, the team led by Ronald Hansen aimed to close those gaps. The room was not dramatic to look at. Tables dense with optical equipment, black cables curled like sleeping snakes, red laser dots trembling faintly, vacuum chambers sealed with polished flanges. Yet beneath the quiet hum was a careful choreography timed 2/billionths of a second. The experiment would use pairs of electrons trapped in tiny diamonds, separated by over a kilometer of fiber optic cables stretching under the university's grounds. These electrons would be forced into a single quantum state, entangled so that measuring one would instantaneously influence the other, even though no classical signal could travel between them fast enough. Critics had long argued that maybe detectors were biased. Maybe light speed wasn't beaten because hidden information had time to pass. Maybe human choices of how to measure weren't really free. Hansen's group set out to block every excuse. They arranged two labs far apart, each with its own entangled electron and detection setup. Random number generators decided measurement settings at the last instant. It's fast enough that no signal could coordinate the outcomes. The electronics were tested, shielded, timed with extraordinary care. When the data finally came in, after long hours of calibration and nights of running trials, The result was clean and unambiguous. Correlations between the distant electrons violated Bell's inequality in a way no local, hidden mechanism could explain. Entanglement, as bizarre as it sounded, was not a fragile rumor, but a robust fact of nature. In physics, this was a triumph, closing what experts call the loophole problem of Bell tests. Yet for anyone thinking about consciousness and the brain, it was also a quiet beacon. If two particles can share a single state across distance without any signal passing between them, and if this link can survive real-world noise, then the quantum world is not as delicate and brittle as once feared. It can stretch, persist, and remain coherent long enough to do work, even outside pristine cryogenic labs. That matters because one of the strongest objections to quantum theories of mind, including Penrose and Hameroff's microtubule speculations, has always been that the brain is warm, wet, and messy, an impossible place for quantum effects to last. But the Delft work and other modern experiments suggested entanglement is not as easily broken as we thought. Nature, it seems, can keep the weird alive. To imagine the scene helps. Technicians hunched over glowing screens. A faint tick of timing circuits. The chilled glass where diamonds hold electrons steady while kilometers away, another lab mirrors the effort. Outside, bicycles clattered over cobblestones, and the city went on with its quiet night. Unaware that deep inside this building, one of Einstein's last doubts was dissolving, the experiment did not mention consciousness. Its goal was pure physics. But for anyone asking if the mind might depend on quantum events, it removed one more reason to say no. Entanglement, once thought too fragile, had shown itself hardy. This does not mean our thoughts are entangled across the skull or that awareness rides some instant quantum link. Scientists remain careful. The leap from electrons in diamonds to neurons in the cortex is enormous. Yet the Delft breakthrough expanded the map of what is physically possible. It showed that quantum coherence and entanglement can survive measurement and noise if handled with the right conditions. Perhaps evolution, working across eons, could find pockets of stability inside the brain's intricate proteins, where subtle coherence flickers just long enough to matter. In the years since Delft, other labs have pushed further. Researchers entangled light across cities, tested quantum keys between satellites and ground stations, and found coherence in biological systems thought too chaotic for such delicate order. Migratory birds seem to sense Earth's magnetic field through entangled electrons in their eyes. Photosynthetic complexes in plants move energy with quantum efficiency, even at room temperature. Each discovery chips away at the old certainty. Life is too hot and noisy for quantum rules to play a role. For consciousness studies, the significance is more mood than proof, but mood matters. The stubborn fact of anesthesia, the strangeness of near-death recall, the hard problem of how matter becomes experience, all of these have long needed a physics willing to allow unusual stability. Delft's experiment whispered that the weird can survive, that coherence can stretch across kilometers, that entanglement is not magic, but a real tool nature uses. If it can persist between diamonds in noisy rooms under ordinary air, perhaps it can persist for a fraction of a second inside microtubules or other biological structures. Enough to tip the balance between unconscious machinery and the spark of lived experience. Standing in the Delft lab after the data confirmed what decades of theory had promised, Ronald Hansen reportedly felt a quiet awe rather than triumph. The numbers were clear, the loopholes closed, yet the deeper meaning remained mysterious. Physics had proved its own strangeness. Reality at its base does not care about distance the way we once thought. And for anyone searching the edges of the mind's story, that night opened a new door, not a doorway with answers, but one wide enough to imagine the brain as part of this same deep, non-local world. It is easy to walk away from these experiments and return to ordinary life. To coffee and bicycles and screens, forgetting the faint, luminous thread that tied two distant electrons together without any visible bridge. Yet somewhere in the back of the mind, the image lingers, if the fabric of reality can hold such silent connection. Maybe the boundaries we assume between here and there, between self and world, are thinner than we think. The Delft night did not prove consciousness quantum, but it made the question harder to dismiss. And in science, that is often how revolutions begin. Snow falls softly against stone walls where butter lamps flicker and incense curls upward, filling the cold mountain air with a faint, sweet smoke. In a remote Tibetan monastery, monks sit cross-legged in long rows, their robes pooled like dark rivers on the floor, breath slowing until the room itself seems to breathe with them. For centuries, these men have trained the mind to hold silence without losing awareness, to watch thoughts arrive and fade like wind-blown snow. Long before Western science named brain waves or neural oscillations, they spoke of clarity and stillness, of the ability to remain awake inside, deep calm. It was an inner landscape, mapped not with instruments, but with practice that's often lasted decades. By the late 20th century, these quiet traditions found an unlikely visitor, the modern neuroscientist, arriving not with prayer beads, but with laptops, electrodes, and scanners. Curiosity had grown as reports emerged of extraordinary mental control among advanced meditators, slowing heart rate, holding attention for hours, even altering perception of pain. What might the brain look like in such states? Could there be measurable signs of something special when the mind turns inward with unusual skill? In the 1990s and early 2000s, teams led by people like Richard Davidson from the University of Wisconsin and Antoine Lutz began traveling to monasteries and inviting monks to research centers, seeking to capture with magnetoencephalograph, or MEG, what centuries of training had wrought. MEG is an exquisitely sensitive tool. Instead of measuring electrical potentials on the scalp like EEG, it detects the faint magnetic fields produced by neuronal currents themselves. The devices look almost otherworldly, a large white helmet studded with sensors, surrounded by shielding to block the stray hum of the modern world. Participants sit or lie very still as the machine records, moment by moment, the whispers of millions of neurons firing together. The signals are fragile. Even a passing elevator can spoil them, so the rooms are built like deep vaults, lined with metal to guard the quiet. When experienced Tibetan practitioners entered these scanners and began their meditation, often compassion practice or open awareness known as Rigpa, something remarkable appeared. Normal waking brains show a patchwork of rhythms, some fast, some slow, not always in step. But under deep meditation, the patterns shifted. High-amplitude gamma oscillations, extremely fast but normally fleeting, bloomed across the cortex in unusual strength and synchrony. Davidson's group reported these findings around 2004 in proceedings of the National Academy of Sciences, startling colleagues who expected relaxation to mean simply slower waves. Instead, the monks' brains looked not quiet but finely orchestrated, like 1,000 instruments suddenly tuned and playing together. The subjective accounts matched the data. Practitioners described vast, vivid awareness, without distraction, a sense of unity and intense presence. It was not blankness, but clarity. And the objective picture suggested a kind of large-scale coherence, brain regions far apart acting as one system rather than separate noisy clusters. Scientists debated what this meant. Some argued that such synchrony might simply support attention and integration of sensory and emotional systems. Others, more adventurous, wondered whether the disciplined mind was somehow stabilizing extremely delicate processes that under normal conditions collapse too quickly to matter. Here the conversation brushes against the quantum question, though carefully. If microtubules or other tiny neural structures can sustain fleeting quantum coherence, perhaps only a very ordered environment, low internal noise, synchronized firing, would allow those effects to add up. Meditation, with its long, gentle training of attention and bodily calm, might reduce chaos and amplify subtle patterns. The monks were not thinking of quanta or superpositions, but their discipline could incidentally create a biological setting where fragile physical order lasts longer. The possibility is speculative but intriguing enough that some physicists and neuroscientists quietly discuss it when data from these extraordinary subjects are presented. Outside the scanner rooms, the images are memorable. Men in maroon and saffron robes, stepping from the cold into humming research centers. smiling shyly at engineers, then sitting for hours while machines listened to their living silence. Some of the earliest sessions required improvisation. Monks used meditation cushions brought from monasteries. Researchers offered tea between long runs of data collection. There was a cultural exchange, too. Western scientists discovering the patience of a tradition that had mapped the mind without instruments, and monks curious but not troubled by the idea that their inner training might be measurable. What has emerged is not proof of any grand theory, but a deepening respect for the plastic, trainable nature of the human brain. Meditation seems able to reshape neural connectivity, dampen reactivity, increase integration in ways ordinary waking life rarely does. Some researchers, including Hameroff himself, have pointed to these results as suggestive. If consciousness depends on delicate micro-events, perhaps certain states make them more coherent, less drowned by noise. Others remain cautious, noting that synchrony and gamma rhythms can be explained within classical neuroscience. But few now deny that long training can produce extraordinary and stable patterns of brain activity. The sight of a monk stepping out of the Meg helmet, serene and lightly smiling, remains quietly powerful. Here is a person who has learned to navigate the snowfields of the mind, broad white silence. Crisp but alive, and here is modern science catching a faint trace of that journey in magnetic whispers. It does not answer what consciousness is, but it shows that awareness can be shaped, heightened, calmed, and perhaps tuned for the larger story of mind and quantum physics. This matters because it proves the brain is not fixed. Its noise level, its internal harmony, can change under will and practice. If there is any truth to the idea that quantum order needs shelter to survive, then practices that quiet turbulence might open tiny windows where the improbable can persist. That alone gives reason to keep looking, to bring together ancient introspection and the most sensitive instruments we can build. So the snowfields remain white, silent, inviting, but no longer untouchable by study. Somewhere between a prayer hall at 4,000 meters and a shielded room in Wisconsin or Lyon. The oldest questions of the inner life have met the newest questions of physics. The answers are still beyond reach. But the conversation grows richer, the wonder more disciplined, and the possibility that the mind is a far stranger landscape than we guessed becomes harder to ignore. Deep. Where polished metal benches hold microscopes that seem more like space telescopes turned inward, the brain has been revealed in ways no earlier age could have imagined. At ordinary scale, a neuron under a light microscope is beautiful enough, a delicate body with threads reaching in all directions, the famous branching dendrites like bare winter trees. But when scientists began pushing electron microscopy to its limits, bathing thin slices of cortex in heavy metal stains, and tracing their interior with beams of electrons, the familiar forest of neurons transformed into something almost unearthly. Within those cells, the scaffolding is not just tangle and mess, but an intricate crystalline order, lattice of proteins stacked and braided, twisting like well-built trellises for signals to climb. The deeper one peers, the stranger it feels. As if the living tissue were part cathedral, part circuit board. Among these inner structures, microtubules stand out again, long hollow cylinders, only a few nanometers across, yet reaching great lengths through the cytoplasm like tiny highways or bones for the cell's body. Under certain preparations, they glitter faintly with regular rings and spirals, rays of tubulin proteins locked together in a geometry so precise it looks machined. In high-resolution images from the 2000s, some show ordered hexagonal sheets wrapping to form tubes, the patterns suggestive of something built rather than merely grown. Researchers who spend their lives mapping synapses sometimes pause in quiet wonder at this secret. Architecture orchards of structure hidden inside each neuron. Orchard after orchard repeating by the billions across the human brain, light itself behaves. Strangely, when it meets such complexity, in advanced optical studies, tiny flashes scatter and dance. Interference patterns bloom and vanish, and faint whispers of what physicists call quantum noise emerge. The random but patterned flutter of energy at scales. It's too small to see. Vibrations pass through these protein lattices as well. Ultra-fast and delicate, like the shimmer of sound through a violin's wood, but much finer and swifter. Some measurements suggest these vibrations can be coherent, meaning they act together rather than chaotically, at least for brief moments before the warmth and bustle of the cell wash them away. In principle, such fleeting order could serve as a stage where something subtler than ordinary chemistry plays out. It is here that science bends into its own sort of poetry, even as it tries to stay disciplined. We know neurons fire electrical pulses and release neurotransmitters at synapses, the familiar mechanical side of brain function. But beneath those well-mapped events lies a quieter world where geometry and vibration and quantum possibility mingle. Roger Penrose and Stuart Hameroff built their ideas on this very territory, arguing that these protein orchards, deep inside neurons, might be the right kind of place for quantum states to arise and briefly persist, though their orchestrated objective reduction theory remains unproven. Simply seeing the fine architecture of microtubules and associated proteins lends their speculation a visual anchor. The brain is not a loose sponge of jelly. It is exquisitely built at scales where quantum physics lives. Yet the wonder of these images does not require one to accept any single theory. Even the most conservative neuroscientists, who keep to well-established electrical and chemical models, admit that the richness inside a cell far exceeds what most textbooks once implied. Synapses are not just on-off switches, but complex molecular machines. Cytoskeletons are not just beams, but dynamic networks. The living brain is a mechanical miracle, yes, but one that almost seems ghostly when seen at this depth. Shimmering fields of ordered protein, lit by scattering photons and flickering, the statistical noise of the quantum world. The laboratories where this is studied have their own quiet drama. Technicians slice tissue thin enough to float in fixatives, mounted on tiny grids, and slip it into the vacuum chamber of transmission electron microscopes. On screens emerge landscapes no human eye could ever see directly. Sweeping dendritic shafts studded with synaptic vesicles. Rows of microtubules running like well-laid rails. Dense knots of actin filaments twisting among them. Researchers trace these by hand and algorithm, building digital maps so detailed that entire neighborhoods of cortex can be reconstructed in 3 dimensions. When zoomed in far enough, the individual proteins line up like beads ordered but alive, vibrating in ways our best models only begin to describe. Occasionally, in papers or conference talks, scientists show animated fly-throughs of these reconstructions. One moment you drift through a forest of synapses. Next you tunnel down into a single axon filled with microtubules and mitochondria, and still deeper until you are surrounded by repeating latticework. Some viewers feel awe, others discomfort, because to look closely at the machinery of mind is to face the gap between what is there and what it somehow gives rise to. The diagrams are silent, yet from them comes music, thought, grief, joy. How does this happen? Quantum physicists who peer at the same scale find something familiar in the flicker and order. The vibrational modes of proteins are not entirely random. They can form standing waves. And some calculations suggest that brief quantum coherence, the same delicate phenomenon used in photosynthesis and perhaps bird navigation, could exist in these ordered microstructures for picoseconds or longer. That is unimaginably brief to us, but in the rapid dynamics of molecular life, it may be enough to matter. Enough to influence how signals cascade, whether these ghost signals have anything to do with consciousness remains a question. But their very possibility stretches imagination. If the mind is both ghostly and mechanical, perhaps it is because the ghost is not outside the machine, but threaded through it, rising when countless tiny events find fleeting harmony. Microtubules, with their crystalline beauty, might be part of the hidden stage. Other players, unknown, may join the dance. For now, the images speak their own truth. The brain is stranger and more intricate than we once believed. It is an orchard of impossible trees, each branch a living lattice built from nanoscopic parts humming with energy. Light scattering off unseen surfaces, vibrations whispering in darkness. To watch these scenes unfold on a researcher's screen is to feel the weight of a question that centuries have not answered. The self that wonders, dreams, and speaks lives somewhere in this shimmering interior. Whether quantum order is its secret or not, the journey into these ghostly fields is already reshaping how we think about thought itself. In the uneasy years after the Second World War, as the rubble of Europe hardened into new borders and the horizon filled with the shadow of nuclear standoff, the study of the human mind found itself drawn into currents far beyond the university. Governments that once left philosophers to quiet argument began to look at consciousness with a calculating eye. The Cold War was as much a contest of control and influence as it was of missiles. And to some strategists, the brain itself seemed the next frontier. Into this climate spilled an odd mixture of curiosity, secrecy, and fear that shaped what questions could safely be asked about awareness for decades. By the early 1950s, the United States had begun pouring funds into research on behavior and cognition, often under the broad banner of psychological operations. Public programs studied learning and memory. Quieter ones studied manipulation. The CIA's infamous MKUltra project, launched in 1953, drew from this mood. Although it is now mostly remembered for its reckless experiments with LSD and hypnosis, its broader aim was to probe whether consciousness could be broken, reshaped, or even directed by chemical or psychological means. Scientists of real standing found themselves asked to investigate sensory deprivation tanks, hallucinogens, subliminal influence, not to answer philosophy's ancient puzzle, but to build resistance against enemy interrogation and to search, however faintly, for tools of persuasion and control. Parallel efforts stirred in the Soviet Union. Reports reached the West of psychotronic research and claims of telepathy or remote influence, often wrapped in grandiose language but taken seriously enough that American agencies felt they could not ignore them. The fear was not that such powers had been proven, but that ignoring even a remote chance could mean strategic disadvantage. Funding flowed to test remote viewing, the idea that a trained mind could describe distant scenes without sensory contact. The Stanford Research Institute in California, under contract with U.S. intelligence in the 1970s, quietly hosted experiments where subjects tried to visualize secret Soviet installations. Some produced oddly accurate sketches. Most did not, and rigorous analysis remained skeptical. Yet the money kept coming for a time because, in the cold logic of geopolitics, even one success could matter. This climate shaped mainstream neuroscience too, though less obviously. The most respected laboratories stayed far from anything that smelled of mysticism or untestable speculation. Academic careers depended on appearing solidly empirical, a stance sharpened by the suspicion that any talk of consciousness could slide toward the kind of psi research mocked in elite journals. Funding agencies preferred safe topics: vision, motor control, reflexes, later computational models of cognition. Even as quantum physics was remaking our understanding of matter, to suggest quantum mind processes in those decades was professional risk. Better to study neural networks as information processors and leave the hard problem. Of subjective experience aside, still, behind closed doors, curiosity survived. The RAND Corporation, a think tank tied to the U.S. Air Force, quietly reviewed literature on altered states and their possible applications. NASA and the military looked at biofeedback and meditation as tools to sharpen attention or resist stress in astronauts and pilots. The very monks who would later sit under MEG scanners first came to Western attention, partly because the military wondered if deep calm might be trainable and useful. But these interests were usually couched in practical terms: performance enhancement, interrogation resistance, not in the language of wonder about awareness itself. By the 1970s and early 1980s, sort of brain war mood had settled. Cognitive science was blooming, computers were reshaping metaphors of the mind, and yet a hush hung over deeper questions. Researchers who asked about the fundamental nature of consciousness often found grant proposals denied or papers dismissed. Too soft, reviewers would write, or philosophical speculation. When Roger Penrose began speaking publicly about the limits of computation in the 1980s, he did so from the shelter of a powerful reputation in mathematics and physics. Younger scholars could not have risked it. Stuart Hameroff, too, found his early speculations greeted with sharp skepticism. some of it scientific and some colored by this lingering political allergy to anything resembling the old Cold War fringe. At the same time, secret programs persisted quietly, even as official ridicule flourished. Declassified documents later showed continued interest in remote viewing under names like Grill, Flame, and Stargate until the mid-1990s. The Soviets had their own counterparts, including research into brainwave synchronization and biocommunication. Much of it was inconclusive. But its existence reinforced a strange double standard. Governments could investigate extraordinary claims behind closed doors, while public science had to avoid them to protect credibility. This political weather mattered because it sculpted the field's intellectual map. For decades, the safe path was to describe the brain as an advanced machine, to map inputs and outputs, to simulate attention and memory on computers. Questions about subjective being, why there is something it feels like to be alive, were politely deferred or mocked as not yet science. Quantum consciousness proposals, dream studies, near-death experiences, meditation, research, all hovered at the edges. Pursued by a few but largely exiled from mainstream support, and yet, despite the pressures, curiosity found cracks. The end of the Cold War and the slow declassification of intelligence. Experiments revealed to younger scientists how much had been quietly explored. Meditation studies gained legitimacy when stripped of mystical claims and framed in terms of stress reduction and neuroplasticity. Journals tentatively opened space for serious discussion of consciousness. Spurred by conferences like Toward, Science of Consciousness begun in the 1990s, the political fear that asking deep questions might serve an enemy began to fade, replaced by a more ordinary scientific caution. Looking back now, the irony is clear. Some of the most exotic and imaginative exploration of consciousness during the 20th century happened not in philosophy departments, but in rooms funded by defense budgets and shielded by classification. Yet that very secrecy and later backlash built a stigma that slowed open inquiry for years. The brain wars, fought partly in shadows and partly in academic halls, taught an enduring lesson. Politics can dictate which mysteries we are allowed to approach without risking our standing. For the modern conversation about quantum mind theories and the subtle physics of awareness, this history is a quiet caution. Ideas like those of Penrose and Hameroff were not just judged on evidence, but on the lingering scent of Cold War speculation. To study consciousness seriously required navigating a legacy of suspicion. As that weather clears, slowly, more scientists feel free to ask again what the mind really is and how deep its roots may go. Without fear of being mistaken for covert operatives or mystics. But the imprint of those decades remains. Reminder that the path to understanding our own awareness has never been purely about science. It has also been shaped by power, fear, the stories nations tell themselves about what knowledge is safe to pursue, in laboratories scattered across the world. Often in unremarkable buildings with fluorescent ceilings and the faint hum of freezers, there have been moments when even hardened researchers paused at what their data seemed to say. They were not chasing the mind directly, not designing grand theories about awareness. Instead, they were following ordinary questions about how life works, how molecules behave, how cells manage feats that seem impossible under simple physics. Yet again and again, the answers pointed to processes so delicate and improbable that some scientists whispered of a deeper strangeness at work. Something pushing past the edges of classical understanding. These discoveries, though not about consciousness alone, have fed the quiet suspicion that nature may use quantum tricks far more widely than we once believed. One of the earliest shivers came from studies of quantum tunneling, a phenomenon so counterintuitive that even experienced physicists sometimes describe it with unease. In simple terms, tunneling means that a particle can appear on the other side of an energy barrier it should not have the power to climb, slipping through like a ghost rather than rolling over like a ball. For decades, tunneling was known in cold, clean experiments with electrons and superconductors, the stuff of low-temperature physics. But in the 1970s and 1980s, chemists began to see evidence that tunneling was quietly shaping reactions inside warm living matter. Enzymes that split hydrogen bonds, for instance, appeared to rely on protons vanishing and reappearing across barriers far too tall for classical crossing. In 1989, detailed work on the enzyme alcohol dehydrogenase suggested proton tunneling at room temperature in the wet interior of cells. It was not supposed to be possible, and yet it seemed to be routine. More recent experiments pushed the thought further. Proteins involved in smell, the receptors in our noses that let us tell rose from smoke, may detect odor not only by shape, but by quantum vibration. Electrons tunneling to sense molecular dance. Such ideas were proposed in the 1990s by Luca Turin, and at first dismissed. Yet new data slowly gathered support. The implication was that our most basic perceptions might lean on effects long assumed too delicate for biology. Then there were the cold frogs. Biologists had long known that certain animals survive freezing winters by slowing metabolism to almost nothing. But careful work on wood frogs in North America revealed something more astonishing. These frogs can endure being frozen solid for days. Their hearts stopped, their blood turned to ice, and yet returned to life when warmed. To do so, their cells must endure stresses that shred most membranes and proteins. Studies in the late 20th century found that cryoprotectants like glucose and urea flood the frog's tissues, stabilizing structures. But hints emerged that quantum tunneling may help repair or protect key bonds during the freeze-thaw cycle. As if the fabric of molecules quietly rearranges itself beyond normal thermal jostling. The survival of such creatures in conditions fatal to most complex animals became a kind of living demonstration of nature's hidden resourcefulness. Photosynthesis added another deep tremor. In 2007, using ultrafast spectroscopy at Berkeley Lab, researchers saw that light energy captured by plant cells travels through a quantum superposition, a state where it explores many possible routes simultaneously before landing. In the best possible spot to drive chemical change, this coherence persisted far longer than anyone believed possible in warm, wet tissue. It was as if the leaf were running a quiet calculation beyond classical reach to squeeze every bit of sunlight. That same decade, physicists studying migratory birds found evidence that entangled electrons in cryptochrome proteins might be giving birds a built-in compass, sensing Earth's weak magnetic field with quantum sensitivity, for those already wondering if the brain might harness unusual physics. These scattered findings formed a kind of background music. No single one proved anything about consciousness. But together they dismantled the old claim that quantum effects are too fragile for biology. Life, it seemed, had been using them all along, hidden in ordinary processes. If tunneling can shape enzyme reactions, if coherence can survive in leaves and bird eyes, perhaps neurons, too, have found ways to shelter subtle events long enough to matter. Some of the work has been eerie enough to unsettle the scientists themselves. In experiments with photosynthetic complexes cooled and probed by femtosecond lasers, the coherent wave-like signals persisted even when researchers heated samples to near body temperature, a result so unexpected that labs repeated the tests again and again before daring to publish. Quantum signatures refused to vanish in messy, living-like conditions. When these findings emerged in journals like Nature and Science, more than one physicist admitted discomfort. The barrier between life and fundamental physics had just grown thinner, and deep in anesthesiology labs, other unsettling data appeared. Certain anesthetic gases seemed to act not by blocking synaptic chatter but by altering electron behavior in hydrophobic pockets of proteins, potentially the same sorts of quantum-sensitive places Hameroff had long speculated about. It was as though turning off consciousness might indeed involve nudging tiny physical states that we cannot yet fully describe through. It all runs a feeling that nature is quietly more clever than our first theories allowed. The warmth and wetness once used to dismiss quantum speculation have turned out not to be automatic death sentences for coherence. Organisms seem to have evolved microenvironments, shielded protein pockets, ordered water layers, stable lattice where improbable events can last just long enough to be useful. Perhaps cells have done so for billions of years without our noticing. These experiments frighten some not because they hint at ghosts, but because they force humility. We thought we understood the limits of the small and the living. We did not. They also nourish a quiet daring in those who want to ask bigger questions about the brain. If tunneling and entanglement thrive in leaves and frogs and noses, who is to say the neurons inside our heads do not play by similar rules? The mind may still be largely unexplored country, an orchard of cells whispering across thresholds we barely know how to measure, so the researchers keep probing. Lasers flashing in darkened rooms, magnetic sensors poised, computers logging strange correlations. Many remain skeptical of grand claims about consciousness, yet few now say with certainty that the quantum world stops at the skull. What once seemed impossible is proving to be part of life's deep grammar, and that recognition, quiet but unstoppable, is enough to unsettle even the steadiest scientist, the realization that the universe has been weaving subtle patterns through our cells all along. While we were just learning to listen in the early 1980s, in a quiet San Francisco laboratory far removed from the drama of particle accelerators or brain surgery, a series of experiments began that would trouble anyone who has ever believed their choices are entirely their own. The work was led by Benjamin Libet, soft-spoken neurophysiologist at the University of California, San Francisco, who had spent his career studying the fine timing of brain signals. Libet was not looking for controversy. He was curious about something simple but profound. When you decide to move, to flick your wrist, tap a finger, speak a word, when does that decision actually happen? Does the conscious urge come first, as it feels, or does the body begin before the mind knows? His setup was modest but ingenious. Volunteers sat in a dim room with electrodes on their scalps, connected to an electroencephalograph, while their eyes watched a fast-moving sweep around a clock face projected on a screen. They were asked to wait and, at any moment they wished, flex a finger or flick a wrist. Then remember where the dot was when they first felt the urge to move. Meanwhile, the electrodes traced their brain's activity, especially a slow buildup called the readiness potential, a ramping electrical signal in motor regions, known since the 1960s to precede movement. The results startled everyone, including Libet himself. Time after time, the readiness potential began its slow rise about 550 milliseconds before the actual muscle movement, more than half a second before action. But the reported moment when participants became aware of wanting to move came only about 200 milliseconds before the action. In other words, the brain seemed to gear up long before the person felt the decision. By the time you think now, your neurons have already been preparing. Libet was cautious, but clear in describing the implication. Consciousness might not initiate voluntary acts so much as monitor and, perhaps at the last instant, vetoed them. He called this free won't, the idea that while we might not start impulses consciously, we can still stop them before they reach the muscles. But many who read his 1983 papers in Brain took a darker lesson. Maybe the feeling of free will is an echo, a story the mind tells after the machinery has already moved. For a public raised on the sense of an inner captain steering the ship, this was unsettling. Newspapers seized on headlines like "Brain knows before you do." Philosophers argued late into the night, if the neurons act first, are we nothing but passengers? Some defended freedom by pointing out that Libet's tasks were trivial. Flicking a wrist is hardly the same as choosing a career or forgiving a friend. But the discomfort lingered at the edges of neuroscience and physics. The conversation took another twist. Libet himself, though not a quantum physicist, wondered aloud whether the mysterious indeterminacy at the smallest scales might play a role. Perhaps the readiness potential represents the brain setting the stage. But the final collapse of quantum possibilities, the jump from maybe to yes, could still allow conscious intervention. His speculation was cautious, almost reluctant. But it seeded a question: could the haze before a decision, that half-second of unconscious buildup, be a place where tiny, not-determined events influence the outcome? If the neural preparation is probabilistic rather than fixed, maybe awareness nudges which branch becomes real. Later thinkers, sympathetic to quantum models of consciousness, took up the thought. Stuart Hameroff and Roger Penrose, already arguing that microtubules might sustain fragile quantum states, suggested that these pre-movement signals could be where orchestrated. Objective reduction operates where collapsing superpositions could tilt one way or another. If so, free will would not be abolished but reframed, not a cartoon captain commanding neurons, but a subtle, moment shaping of probability within a prepared field. Skeptics responded that no exotic physics is needed. The brain is a complex self-organizing system and can generate decisions without a central decider. Modern imaging has extended Libet's work with studies by John Dylan Haynes in Berlin using fMRI to predict up to 7 seconds before a simple choice which button someone would press. Yet even these long lead times are not absolute. Predictions are statistical, and subjects can still sometimes surprise the model. That sliver of unpredictability keeps the debate alive in the dim rooms where Libet worked. The atmosphere was not triumph, but quiet unease. Students watched the flickering IG traces and felt their own hands twitch almost before they knew. The hum of equipment seemed to underscore a strange loss, the cherished feeling that the I who decides is fully in charge. Yet Libet himself urged patience. He noted that consciousness can intervene once an impulse begins. A half-second is enough to stop harm, to reshape action. He also argued that deeper choices, built over seconds or minutes, might involve loops of feedback where conscious reflection and unconscious buildup intertwine. The picture is more layered than a single moment of now. Still, the experiments left a mark. They cracked the comfortable narrative of free will and opened a space where physics and philosophy meet. If consciousness is not the prime mover, but a complex participant in brain events, we must rethink what choosing means. And if the physical substrate of those events includes quantum-level uncertainty, then our sense of authorship might rest on the way tiny probabilities resolve inside living tissue for those exploring the quantum mind. Libet's data became both caution and invitation. They warned that simple stories of control are naive, but they also suggested a place, that half-second of preparation, where something subtle and perhaps indeterminate happens. It is a window where the future is not yet fixed, where chance and structure meet and where some hope. The subjective experience we call intention might reach back into the machine. Walking out of Libet's lab after a session, volunteers often described a faint vertigo. They had felt themselves act, but the graphs told another story. It is a feeling that lingers, as if the self is partly an afterimage, yet somehow still real. That unsettling duality, being both the watcher and the watched, is perhaps the truest legacy of the readiness potential. It shows that the road to understanding consciousness winds through shadows, where cause and effect blur, and where freedom may be quieter and stranger than we were taught, but not necessarily gone. Across long centuries, before laboratories and superconducting magnets and brain scanners, men and women sat in desert caves, forest shrines, and high mountain cloisters, trying to name what it felt like simply to be alive. They had no measurements, only the disciplined attention of quiet minds and the hard-won vocabulary of poetry and prayer. Yet again and again, scattered across cultures and eras, certain patterns of insight appeared as if carried by a common current. The great Buddhist teachers of India and Tibet spoke of unetta, no enduring self, only a stream of events, sensations, and thoughts without a permanent core. The sages of Advaita Vedanta in southern India described an even stranger vision, that behind the play of separate persons and objects, there is a single field of awareness. Brahman, not divided, not local. The quiet ocean from which individual experience rises like waves and to which it returns. In the Christian West, mystics like Meister Eckhart in the 13th century wrote of a divine spark, a point of luminous knowing beyond the ego, older and deeper than the personality that comes and goes. Sufi poets in Persia, Neoplatonists in Greece, Taoist masters in China, all seem to circle the same ineffable center. The small eye is porous and not ultimate. Something larger moves through it. For most of history, these ideas remained within monasteries and esoteric circles, woven into ritual and metaphor rather than analysis. Yet they carried a paradox that feels familiar to anyone who has brushed against modern physics. If the self is not a fixed little thing, if the boundaries we assume are not real, then what we experience as me could be more like a pattern, a temporary standing wave in a deeper field. That image of a field of dynamic interconnection runs uncannily close to what quantum theory now says about matter and space, the Buddhist teaching of dependent origination, that each moment arises because of countless prior conditions and cannot stand alone, resonates with the quantum view that particles have no independent existence but are excitations of underlying fields and defined by their relations. Advaita's insistence that all consciousness is one, that the apparent separation of minds is illusion, sits strangely beside discoveries of non-locality and entanglement, where events distant in space show an unseen unity. Eckhart's spark beyond time and form feels not unlike what physicists mean when they say the classical world we see is a late crystallization, a collapse out of a far subtler reality that is not bound by our ordinary measures of time and distance. Of course, these parallels are not perfect. Ancient masters were not talking about Planck constants or Bell inequalities. They were speaking from lived introspection, yet the overlap is hard to ignore. When people sat still enough and long enough to watch the mind, they often reported its transparency and its odd field-like quality. When scientists looked deep enough into matter, they found similar slipperiness, no solid core, only probability, interrelation, and emergence. In recent decades, scholars have begun to trace this dialogue more carefully. The Dalai Lama, intrigued by neuroscience and physics, invited researchers like Francisco Varela and Richard Edson to discuss brain rhythms with monks trained in centuries-old contemplative practice. Conferences in Dharamshala in California brought together quantum theorists and Tibetan abbots. Some exchanges were awkward, each side protective of its own terms, but there was also wonder. That highly disciplined subjective exploration and highly disciplined objective measurement might be meeting at a shared edge. Western mysticism, long neglected in science's rise, has been reread with new eyes too. The language of negative theology, the cloud of unknowing, can sound like the physicist's caution about describing quantum reality. Medieval Christian contemplatives often warn that ordinary self and world are not final. Beyond them lies a presence that cannot be mapped but is somehow foundational. When John of the Cross spoke of the dark night that precedes union, when Eckhart said the soul must become empty to touch the divine ground, one hears faint echoes of letting go of classical certainty to meet something more subtle. The cross-cultural bridge matters not because it proves anything about physics or consciousness, but because it reminds us how long humans have felt this strangeness inside. The hunch that identity is not ultimate, that awareness is connected and elusive, is older than our machines. Now, as quantum models of mind gingerly appear, as microtubules and coherence and non-localities slip into the conversation, it is hard not to feel a resonance, perhaps. We are circling an ancient insight with new instruments. There are moments in modern labs that almost feel monastic. A physicist, alone at 2 a.m, waiting for entangled photons to trigger a detector, sits in a kind of vigil. A neuroscientist staring at gamma rhythms from a meditating monk is watching for something just beyond the graphs. They may not speak of the soul or the one mind, yet their search touches the same mystery. Both traditions, the contemplative and the scientific, know the discipline of patience and the humility of partial knowledge. It would be easy, and wrong, to collapse these worlds together too quickly. Science must remain careful. Old metaphors cannot replace data, but it would also be foolish to pretend the echoes do not exist. They suggest that the human nervous system, long before fMRI, could sense truths about its own transparency, and that when quantum theory describes a world of interrelation and collapse, it may not be inventing, but rediscovering a pattern felt in meditation halls and desert cells for millennia. In this sense, the modern inquiry into consciousness is not starting from nothing. It is a new chapter in a much older conversation. Where once people used Sanskrit or Latin or Persian verse, Now we use mathematics and imaging. Where once one sat before an altar or an open sky, now we sit before data screens. But the question is the same. What is this I that thinks it decides, and what is the vastness in which it appears? Each step closer to understanding, whether through quantum biology or practice, seems to confirm that the self is thinner, the world more connected, and the ground of experience far stranger and deeper than we thought. And long. Windowless rooms where the air is cool and faintly sweet, with the scent of growing things kept under artificial light, a quiet revolution has been taking place. Here on steel benches crowded with cables and delicate glassware, scientists have spent the last 2 decades asking questions that once seemed impossible. Can living systems, warm and wet and endlessly jostled by thermal noise, maintain the fragile quantum states thought to belong only to the subatomic world? At first, the answer was expected to be no. Quantum effects were supposed to collapse instantly under the rough conditions of biology. But one by one, experiments have returned with a different story, and their implications reach well beyond the leaves and wings they study. The first great surprise came from the way plants drink sunlight. For most of the 20th century, photosynthesis was pictured as a chain of chemical steps, energy hopping like a courier from one pigment, molecule to another, until it reached the reaction center where sugar making begins. But in the mid-2000s, teams at Berkeley Lab and the University of Toronto began using ultra-fast laser pulses, bursts of light lasting mere femtoseconds, a millionth of a billionth of a second, to watch what actually happens when a photon strikes a photosynthetic complex. To their astonishment, they found evidence of coherence. The captured energy seemed to explore many possible pathways at once, a quantum superposition mapping the maze of pigments and picking the most efficient route. These wave-like states persisted far longer than theory predicted, even at room temperature in living-like conditions. In 2007, Graham Fleming's group published results showing coherent electronic oscillations, lasting hundreds of femtoseconds, where none should have survived. A trivial flicker by human standards, yet enough time in molecular terms to change how energy flows. The leaf, it turned out, was running a kind of quiet quantum computation every time light touched it. Not long after, a different mystery unfolded in the night sky along the routes of migrating birds. For centuries, sailors marveled at the unerring navigation of species like the European robin or the Arctic tern. Classical explanations invoked the sun, stars, and landmarks. But experiments suggested birds can orient even when skies are clouded and familiar cues absent. By the 1970s, researchers suspected some sensitivity to Earth's magnetic field, but the physics seemed to faint to explain. Then work on a protein called cryptochrome, found in the retinas of many birds, suggested an answer almost unbelievable. When certain light hits these molecules, they form entangled pairs of electrons whose spin states are exquisitely sensitive to magnetic fields. As the bird moves through Earth's field, these quantum states shift, altering chemical reactions and likely creating a ghostly visual pattern. Overlaying the bird's normal sight, a compass made of entanglement. In 2008 and 2011, studies in Nature and Biophysical Journal deepened the case, showing that these radical pair reactions are robust enough to operate at body temperature. Inside the noise of a living eye, walk into one of the labs chasing these secrets, and you might see potted seedlings glowing faintly green under LEDs, their leaves threaded with optical fibers, or tanks holding tiny songbirds shielded from stray magnetic interference. The gear is not exotic at first glance: coils to create controlled fields, pulse lasers aimed into minuscule samples, spectrometers waiting for light's return. But what they measure is astonishing: faint quantum beats echoing through proteins, coherence hanging on against heat and water, entanglement surviving long enough to shape life's work. For anyone studying the brain, this quiet revolution matters deeply. The old objection to quantum theories of mind was simple: the brain is warm, noisy, and chaotic, so quantum states cannot survive there. Yet plants and birds live at body temperature and manage it. They do so not by miracle, but by clever molecular design, protective cages of protein, ordered networks that shield delicate interactions from disruption. Neurons, it turns out, have their own intricate scaffolding. Microtubules, membranes, ion channels, synaptic proteins. If evolution has already discovered ways to shelter quantum events wherever they prove useful, why assume the nervous system would be an exception? Some neuroscientists, still cautious, now admit that the question is fair. No one claims the brain uses photosynthesis like energy transfer or cryptochrome-style magnetoreception to think. But the broader point is clear. The assumption that life must be strictly classical has fallen away. Warmth and water are not death sentences for coherence if the molecular setting is right. Quantum biology is no longer a fringe phrase, but an active field with journals, conferences, and grant money. Each new result a protein vibration lasting longer than predicted. An electron tunneling across an impossible gap widens the possible space in which neural tissue might operate. The imagery of this work is unexpectedly beautiful. Imagine a bench lined with small cuvettes of chlorophyll solution glowing emerald when the laser hits, each pulse revealing a ripple of energy moving as a single wave through tangled pigment. Picture a robin, tiny and still in a controlled chamber. Its eye bathed in dim blue light as coils sweep a magnetic field around it, the bird tilting its head as if sensing a hidden map. In another wing of the building, chilled cryostats hold protein crystals from the visual system. Their electron spins delicately entangled while instruments listen for faint quantum whispers. Scientists, who started out skeptical, sometimes admit a kind of quiet awe at these results. It is humbling to discover that a leaf has been solving quantum puzzles for billions of years while we only just learned the math. It is sobering to realize that a robin's eye can maintain entanglement across countless molecules, while our best quantum computers still fight environmental noise for the question of consciousness. This unfolding story is not final proof, but a shifting foundation. The walls that once divided too delicate for biology from ordinary living function are crumbling. If a plant cell can choreograph wave-like excitations and a migrating bird can sense the faint tug of Earth's field through entangled electrons, perhaps the neurons that generate thought and perception have also, over deep time, learned to exploit such hidden physics. It does not mean our minds are magical. It means the raw material for magic-like subtlety is available and already used by life. So when we speak of quantum theories of awareness today, the conversation takes place in a new light. A decade ago, it was easy to dismiss. Now, every green leaf and every compass-guided wing is a counter-argument. The shadows under the microscope are alive with faint coherence and strange signals. And while the brain remains vastly more complex than a leaf or a robin's eye, the fact that nature can weave quantum threads into living function gives reason to keep looking. Perhaps within our skulls, too, in the dark orchards of neurons. Similar whispers endure long enough to shape the mystery of being conscious. Stand in a field far from towns and highways on a moonless night, and the first thing you notice is how wide the dark really is. Then, slowly your eyes adjust, and 1,000 pinpoints appear. Each one a small star flaring across impossible distance, their light older than any human life. This image has followed many scientists back into their work. For when we peer into the living brain with its hundreds of billions of cells and trillions of connections, something about it recalls the sky. The cortex spread beneath the skull is not a gray fog but a vast glittering map. Its neurons fire in patterns so numerous and so faint that the comparison to constellations is more than poetic. Each synapse can be seen under the right tools. As a star whose brief spark may join others to form the stories we call thought and memory, in the first decades of the 21st century, advanced imaging made this view almost literal. Techniques like calcium imaging and two-photon microscopy began to record whole populations of neurons, lighting and dimming in real time. Researchers watched activity ripple like auroras across the hippocampus as a mouse ran through a maze. They saw visual cortex flare into quiet constellations when an animal looked at shapes. The maps were not random. They repeated and shifted with experience, just as night skies seem fixed but change slowly with seasons. Each moment of consciousness is such a pattern, a galaxy's worth of tiny events coordinated. enough to create meaning, but so numerous no single one could ever explain the whole at the same time. Deeper physics kept humming in the background, and some began to wonder whether the sky metaphor might hide more than poetry. Light from stars is fragile. It can scatter, fade, yet still reach us across space because of the way waves move together. Something similar might happen in the brain. Beneath the well-known electrical pulses and chemical releases lies a molecular landscape capable of subtler order. Microtubules, membranes, proteins. We have seen them under electron microscopes, latticed and regular, able to support vibrations and perhaps fleeting coherence. These tiny symmetries could let delicate quantum events flicker and persist. Like starlight managing to cross an inhospitable void, quantum coherence, at its simplest, is just unity among possibilities, a system staying in many overlapping states before collapsing into one. For decades, we assumed that warm living brains would scatter such coherence instantly. But again and again, nature has shown otherwise. Photosynthetic complexes maintain coherent energy waves. Bird eyes keep entangled electrons alive long enough to navigate. Enzymes exploit tunneling to speed reactions. If those feats can survive the jostle of life, perhaps neurons have evolved similar shelters, tiny observatories where coherence lasts just long enough to matter. We do not yet know how, but we know better than to declare it impossible. Seen through this lens, the brain's night sky is not just electrical. It may shimmer with a quieter light we cannot yet fully measure. The vast connectome axons arching like the Milky Way, dendritic spines like clusters of stars could be overlaid by an even subtler network of correlations and coherent ripples. Some might last a billionth of a second, some perhaps longer, enough to influence how neurons integrate signals and how patterns of activity coalesce into the fluid continuity we experience as awareness. The human experience of self and world could then be compared to lying beneath that sky and noticing constellations. Our minds pick out shapes and stories from countless points of light, unaware of the deeper physics guiding each photon. We feel as though we choose and know directly, but underneath, vast networks of unconscious preparation and fragile quantum flickers might be setting the stage. It is a thought both humbling and strangely beautiful that our very clarity might arise from a fabric as subtle and ancient as starlight. In practical terms, this picture is beginning to guide experiments. Physicists and neuroscientists now design sensors fine enough to pick up magnetic fields from single axons. Groups at places like University College London and MIT cool and probe proteins that shape synaptic release, looking for quantum fingerprints. Others refine computational models that treat neurons not as simple on-off switches, but as dynamic, wave-supporting structures. These are early steps. The way Galileo's first telescope was crude, but enough to change everything meanwhile. The poetic parallel to the sky continues to help those trying to think across disciplines. It reminds us that scale matters, but does not diminish wonder. A single neuron is small, but billions together form something that dwarfs stars in complexity. And just as astronomers find order in the apparent chaos of the heavens, neuroscientists may yet find principles beneath the seeming mess of firing patterns. The possibility that quantum coherence might be one of those principles is no longer dismissed outright. It is a quiet, plausible maybe, for someone lying awake at night thinking about who they are. These facts and metaphors can merge. The firing of hippocampal cells, as you recall, a summer decades ago. The spread of synchronized gamma waves when you focus. The molecular tremors in microtubules you will never feel. All of it unfolds. As naturally as constellations forming stories in ancient skies, and just as the night sky invites questions without final answers, the brain does too. We can chart more stars, trace more synapses, measure more fields, but the total pattern remains something we live from within, rather than fully explained to look at the brain. This way is not to abandon science, it is to bring awe back into science. The neurons, under glass dishes, glowing with calcium dyes, are distant suns. The quantum ripples in proteins are faint light waves crossing unimaginable spaces. The self reading these words is both mapmaker and traveler. If consciousness is indeed tied to such layered activity, classical and quantum, local and non-local, then our night sky is not above us alone but within us, flickering with mystery at every moment, and so the field waits. Like stargazers before dawn, instruments pointed at faint signals, knowing that each discovery will redraw the map. Perhaps one day, the subtle coherence inside neurons will be charted as surely as constellations are today. Until then, we move forward with curiosity lit by small, persistent lights, both the ones above our heads and the ones firing, silent and uncounted. Inside the living sky of the brain, in the bright lecture halls of Cambridge, in the echoing conference centers of Kyoto and San Diego, the conversation about consciousness today feels both electrified and unresolved. There are roundtables where seasoned neuroscientists and quantum physicists sit side by side, their laptops open to different languages, one full of synaptic models and network graphs, the other bristling with equations about coherence and collapse, yet both trying to describe the same mystery. Interviews in journals and long-form podcasts show this divide as clearly as any microscope. Half the voices insist that the mind is an emergent property of complex computation in wet tissue, nothing more exotic than electrical patterns, while the other half argue that this story fails to explain subjective experience, maybe missing an essential layer of physics. One can hear the tension when someone like Christoph Koch, who has spent decades studying the neural correlates of consciousness, debates researchers sympathetic to Roger Penrose and Stuart Hameroff. Koch will point to careful mappings of the brain's default mode network in integrated information theory, arguing that what we call consciousness is a property of information integration. Meanwhile, Hameroff will reply that none of this explains why information feels like anything. The hard problem David Chalmers, named in the 1990s, remains. And subjective experience is not just computation. Between them sits a generation of younger scientists, many trained in rigorous classical models, yet willing to admit curiosity. They have seen too many surprises from quantum biology to be fully dismissive. Modern laboratories are no longer content to theorize. They are building tools to look. One front line is quantum brain scanning. At University College London and Harvard, physicists and neurologists collaborate on devices that measure magnetic fields at the scale of individual neurons using optically pumped magnetometers. These instruments, more sensitive than traditional MEG, might detect faint quantum signatures if they exist, patterns of coherence that would not show up in ordinary electrical recordings. The idea is still daring and data sparse, but prototypes have already produced astonishingly fine-grained maps of live neural activity, revealing currents once invisible. Another emerging approach is microtubule vibration mapping. Researchers have learned to isolate tubulin structures and strike them with terahertz radiation or ultra-fast lasers to measure their natural resonances. In Arizona, Hameroff's collaborators have been refining techniques to test whether microtubules can sustain coherent oscillations long enough to matter for brain function. Elsewhere, at the Max Planck Institute, teams cool and probe cytoskeletal proteins under near-physiological conditions to see how long quantum states might persist. These efforts are delicate, their results debated, but they represent something new, the move from speculation to direct experiment. Interviews with these scientists often contain a quiet mix of pride and caution. One hears them speak about painstaking months, calibrating instruments to cancel environmental noise, subway trains rumbling miles away, magnetic storms from the sun, because the signals they seek are unimaginably small. Yet one also hears excitement when early data hint at unusual coherence in neural tissue, or when anesthetic molecules appear to damp vibrations at just the right frequencies. These are not proofs, only glimmers. But glimmers matter in a field long starved of direct measurement. On the skeptical side, the arguments remain sharp and grounded. Computational neuroscientists point out that extraordinary claims require extraordinary evidence. They note that current quantum models of the brain are still incomplete, unable to generate clear predictions about perception or memory. They warn against repeating mistakes of the past. when Cold War, a fascination with mind control and parapsychology, discredited careful study. They also highlight the immense complexity of neural networks, even without quantum events. The brain's nonlinear dynamics can produce unpredictability and self-organized patterns that feel mysterious, but are fully classical. Yet what is striking now is that the conversation itself has changed tone. In the 1990s and early 2000s, quantum consciousness was often dismissed outright. Today, it is at least testable. The field of quantum biology has taught humility. Photosynthesis and bird navigation were once thought impossible to explain with quantum coherence, yet they are now textbook examples. This has softened the reflex to declare the brain off-limits. Journals once closed to such topics now occasionally publish careful experimental reports. Conferences on consciousness feature sessions with both camps represented. The feeling among many who follow this work is that we are standing at a shoreline where maps end. The sea ahead is not fantasy but fog, real data beginning to emerge, but no clear shape yet. Some of the fog is technical. Our instruments still struggle to see inside living, firing neural circuits at quantum resolution. Some is conceptual. We lack a theory that unites subjective experience with any physical process, quantum or otherwise. But some is cultural. Science moves cautiously after decades of stigma around consciousness. And reputations remain at stake. In labs late at night, one can sense both excitement and restraint. A graduate student in Boston leans over a bank of detectors, watching magnetic noise fall as shielding doors slide shut. Across the ocean in Delft or Vienna, postdocs adjust cryostats to hold tiny brain proteins steady under laser interrogation. These are not dreamers but careful experimenters, each chasing a thread. They know their work could fizzle. They also know that if even one robust quantum signature tied to awareness appears, the field could shift overnight. Meanwhile, philosophers and cognitive scientists remain engaged, translating new findings into old questions. If quantum processes play a role, do they restore free will or deepen determinism? Does consciousness emerge or is it fundamental, as some panpsychists quietly suggest? Papers circle these issues with careful language. But interviews often reveal something more human, scientists admitting wonder, sometimes even hope, that the mystery of inner life might prove as rich, strange as it feels from within. To stand at this edge is to hold two truths at once. We know far more about the brain than our ancestors did. We can map circuits, read thoughts of movements seconds before they happen, predict perceptions from firing patterns. Yet when we ask why there is something it is like to be, why the lights are on at all, we are still gazing into a haze as deep as the night sky. Our instruments sharpen, our models grow, but the core question remains elusive. And perhaps that is fitting. Every step closer to understanding seems to widen, not shrink. The horizon of wonder, so the work goes on. Long experiments, disputed papers, careful measurements of fragile vibrations, and spirited conversations where skepticism and hope sit uneasily together. There is no grand announcement yet, no single proof, but the fact that quantum consciousness is no longer laughed out of the room signals how far the journey has come. We are close enough to feel the outlines of something new, but still far enough that the fog feels endless. It's a fitting place for any honest search into the deepest mystery we know, the fact that we know it all. In the end, there is a return to quiet. After the long journey through microscopes and lasers, after nights in shielded rooms listening for signals fainter than starlight, after wandering the corridors where mathematicians and mystics sometimes cross paths without meaning to, what remains is the simple rhythm we began with, a single heartbeat, slow and steady, a breath drawing in and letting go. The body sits where it always has, alive and unassuming, yet carrying within it the most intricate experiment any universe has run, the emergence of awareness. For more than a century, modern science has chipped away at the idea that consciousness is untouchable. We have mapped neurons, traced chemical messengers, watched thoughts ripple across the cortex like weather. We have shown that the self is not a fixed island, but a process. One that can be paused, redirected, even silenced for a time, with the quiet drip of anesthesia. We have found hints that the smallest layers of reality, quanta flashing into being and vanishing again, may touch the warm living world far more often than once believed. And yet, for all this, the question that started everything still stands untouched. Why does any of it feel like something? That question remains because every discovery has also widened the horizon. Quantum coherence was supposed to be impossible in life. Then leaves and birds proved otherwise. Free will was supposed to be obvious. Then readiness potentials whispered that we act before we know. Meditation was supposed to be a gentle hobby. Then scans showed the brain remapping itself into unusual order. Each time we reached for a simple answer, the world grew stranger and more subtle, as if reminding us that understanding is not the same as mastery. What has changed is permission. Not long ago, to wonder if consciousness and quantum physics might overlap was to risk your career. Now, careful research programs are being built. There are magnetometers reading neural whispers no one could measure before, lasers searching for vibrations inside microtubules, and journals willing to consider results without easy dismissal. The road is slow and lined with hard skepticism, as it should be, but it is no longer closed. The quantum path is not proven, but it is allowed to exist. When you step back from the instruments and the theories, you can see how human this search has always been. Ancient teachers sitting in silence, 19th century naturalists sketching unknown seas of mind, 20th century physicists cracking open the atom and finding wonder instead of certainty, have been trying to look at the same invisible thing. We have used prayers, poetry, equations, and machines, each one a way to press against the glass that separates knowing from mystery. And perhaps it is right that the answer, if it ever comes, will not feel like an answer. Already we see that consciousness may not reduce to a single switch or location, but is more like a dance. Molecules vibrating, neurons firing, networks weaving signals into patterns that become lived moments. If quantum events feed that dance, they do so in ways subtle enough to defy simple slogans. If they do not, then some other as yet undiscovered layer is at play. Either way, the mystery does not shrink. It only becomes better lit in the quiet after a long day of thinking about such things. It is easy to feel small, but also oddly free. The same universe that makes electrons tunnel and stars fuse also makes a mind able to ask where it comes from. The same quantum fabric that allows light to travel billions of years now folds into the pattern of you, awake enough to wonder. That is not a solution. It is an astonishment. So we come back to heartbeat and breath. We return to the sound of our own lives, moving forward in the dark. There is no final proclamation waiting at the end of this path, only an invitation to keep looking, to keep listening, to hold both rigor and wonder at once. If mind and matter truly are one dance, then every step of discovery is already a step of participation. Each new experiment is not just measurement, but another way of belonging to what we study. And that may be the quiet answer we can live with. The deepest mystery is not out there alone, but here, pulsing behind our ribs, firing in silent constellations of cells, shimmering perhaps with physics stranger than we have words for. We are explorers standing on the edge of the known, peering out, but we are also the thing being explored. The night sky is inside us as much as above us. No one can yet say what we will become if we learn how the dance works. More humble, perhaps, seeing how thin the walls between self and world have always been. More daring, perhaps, building tools that speak with the hidden fabric of life. Or maybe just more awake to the simple miracle that we are here at all, looking and listening. The story is unfinished, and that is its truest beauty.